This video looks at using known resistances to calculate a circuit's length, which is all based around this particular table, which is taken from the on-site guide, the 18th edition Amendment 2 on-site guide in particular, page 218. Now this table gives you the value of resistance per metre or the R1, R2 per metre for copper or aluminium conductors at 20 degrees C. This is table I1. There is actually table I2, which is on the next page, which gives you the correction factors, which are a multiplication factor that you can apply to these figures depending on the ambient temperature. So if the expected ambient temperature is only 5 degrees rather than the 20 that this is given here, you apply a correction factor of 0.94 to these values, which will effectively change the rating to correct for the resistance coefficient per degree C, which is part of the British standard for copper and aluminium conductors. So in order to use this, however, this is quite a useful table and can be used when fault finding. If we take our R1, R2 reading and we get a value, we can calculate the length of circuit from that. And if the length of circuit is known to us and the figure doesn't match, then we know there is a high impedance joint, loose connection somewhere within that circuit. And then we can further break it down using, at the moment we've got R1, R2, where we've got two conductors here, but we've also got the single conductor on its own, which means we could use a Wander lead to take a resistance reading from start to finish on, say, R1 or indeed on R2, and then apply this calculation, which will also tell us the expected length for each leg of the circuit or each conductor R1 and R2. This calculation here allows us to use these values and our known resistance multiplied by this particular factor here, which is a place value correction. As mentioned before, resistance per metre or R1, R2 per metre is in milliohms per metre. This correction factor converts it into ohms, so it's multiplying by 10 to the power of negative 3. If you multiply 1 by 10 to the negative 3, you get 0.001 or 1 milliohm. So that's why we do it like this. And this simplifies the process for converting this into an actual distance. If we take an R1, R2 value of 0.17, we can use this as our known resistance to calculate the meterage of the circuit. A quick word on this is that it is an R1, R2 dead test to get the true R1, R2, as opposed to doing ZS minus ZE. When we do ZS minus ZE, you can't eliminate things like parallel paths, so you don't get a true reflection of this. While you can do ZE add R1, R2 to get ZS, the same isn't true the other way around. It can give you an indication, and if you are doing fault finding and you take a ZS and you already know the ZE, then it will give you an indication of circuit length, but it will not be as accurate as using a dead test. So in this scenario, when we're discussing how to use this calculation, we use R1, R2, dead test, we've got our resistance value there, and we can then add that into this calculation. And for the sake of this example, we're going to look at 1.5 line conductor and 1.5 protective CPC, which is going to be 24.2. So we'll substitute those in, which will look like this. So we've got a known resistance on top. Our value I've labelled A, which is from this column, this one here in particular, multiplied by this. And this is a constant. That value won't change no matter what you're doing. You're multiplying by that, providing you're doing milliohms per metre, of course. So this is what it looks like, but if you were to put it into a scientific calculator or use the scientific calculator on an iPhone, you can type it in this way. So obviously when it's written on top, it's effectively looking like a fraction, and a fraction is just a division. And so we're dividing this by all of this. And so if we put all of this into brackets, it will calculate the brackets and divide this by the answer for this, which will give us this, which is 7.02479 metres. Now, If this is correct, we know that the circuit is healthy. If this figure is not correct, if we know this circuit is perhaps only 5 metres long, then the fact that this is showing us 7 metres implies that this value, there is too much resistance within the circuit, given that this is a constant for a 1.5. So we would be looking for a high impedance joint somewhere within the circuit. It might be within the switchgear. If you've got a rotary isolator in there, one of the poles might be loose. It might be that there is some sort of Vargo connector in there or something along those lines that is not clamped down properly and is high impedance. But it would give you an indication, at least, that the circuit is not healthy, because the length would be calculated to be more than the known length. Equally, the other way around is you can use this to calculate the length of circuits. If you know the circuit is healthy, and you want to calculate how long the circuit actually is, you can use this to calculate it, which could be quite handy if you're running in a new circuit and you know the approximate length, but you actually want to charge by the meter for the cable. You can use this as well. But in terms of then using this to fault find, the R1, R2 being too high doesn't really narrow it down enough for us, because we don't know which conductor the fault would be on. It's just a high impedance for the length of circuit. So what we'd need to do then is we'd use perhaps the R2 wander lead method, null out the wander lead, and then measure just R1. And then we would use 1.5, because it's a 1.5 conductor, this top value, and we'd substitute that in for here. And so if we were getting 0.1 for the line conductor, we'd do 0.1 over 12.10 times 10 to the negative 3, and that will give us the approximate length of the R1 conductor. Well, not the approximate length, the exact length, providing it's all tight and no high impedance joints are in place. You then do the same with R2, and if that is significantly higher, then you know that that is where the fault lies, and so on and so on. So you can then also work back from there. If you find that one leg is higher than the other, given that they should be the same length, and there shouldn't be any parallel paths because you're just dealing with the conductors, then what you then sort of go about doing is using Ohm's law to calculate back, well, what's the distance to fault? And you can actually then take measurements and narrow down to exactly where the fault will occur on the circuit. And so that's how we can use this particular table with this basic calculation to calculate circuit length and verify our R1, R2 values against what the circuit parameters actually are.